it's recording now.
Okay, good.
Okay. So first I'll introduce you my public in Portuguese, and I'll be back to talk to you.
Sure, sure.
Olá pessoal, tudo bem? João aqui. Faz muito tempo que eu não faço um vídeo, né? Que eu tô lá. All wrong. Ok. Olá pessoal, tudo bem? João aqui. Faz muito tempo que eu não trago algum vídeo. E hoje eu tô aqui com o Niles Eldredge para falar de equilíbrio pontuado. Eu espero que vocês gostem. Então, ouçam aí a conversa. Depois vai sair a versão legendada para aqueles que não podem ou que não compreendem inglês, tá bom? Fiquem atentos no canal. Vamos lá, então. Great. Now, I'm gonna read. All right. So, thank you, Dr. Eldredge, for accepting my invitation to this conversation. I'll briefly summarize your career here. Dr. Niles Eldredge has been a paleontologist on the curatorial staff of the American Museum of Natural History since 1969. His specialty is the evolution of trilobites. He published important papers on phacopids specifically. His main professional passion is, of course, evolution. Throughout his career, he has used repeated patterns in the history of life to refine ideas on how the evolutionary process actually works and how it fits with the fossil record. The theory of punctuated equilibria was an early milestone in his career. Dr. Eldredge went on to develop a hierarchical vision of evolutionary and ecological systems. And in his book, The Pattern of Evolution, published in 1999, he unfolds a comprehensive theory, the sloshing bucket, that examines how environmental change governs the evolutionary process. He's concerned with the rapid destruction of many of the world's habitats and species. Dr. Eldredge was curator-in-chief of the American Museum's Hall of Biodiversity and has written several books on the subject. He has also combated the creationist movement through lectures, articles, and books, including The Triumph of Evolution and the Failure of Creationism, published in 2000. A critic of gene-centered theories of evolution, Dr. Eldredge's Why We Do It, published in 2004, presents an alternative account to the gene-based notions of evolutionary psychology to explain why human beings behave as they do. He is author of several papers and books. One book really caught my attention, and it's called Eternal Ephemera, Adaptation and the Origin of Species from the 19th Century through Punctuated Equilibria and Beyond. And today we're here to talk about punctuated equilibria. Again, thanks a lot, Dr. Eldredge.
Oh, my pleasure, João. Thank you for asking me on. It's great.
It's really great for me. So I have about 10 questions to hear your thoughts on them. And I will start with the first one, which I think is the most basic question I can do about, or anyone can do about punctuated equilibria. And it's, what is punctuated equilibria and what is not?
Okay. Punctuated equilibria, when you just look at it coldly and analytically, is two things. It's the recognition that most species, most of the time, are not changing very much. As you collect them, and we can talk about the gaps in the record and all this sort of thing, the overwhelming pattern that meets the eye of a paleontologist is that the species don't change very much, which is very frustrating. At least it was to me 50 years ago when I was trying to do a PhD and looking for evolution and not seeing at first, not seeing very much at all. So it's stasis. This is what we ended up calling in 1972 stasis, which doesn't mean that things remain rigidly the same. It means that there's variation, geographic and within population, of all species, some more than others. And when you go through time, you see that variation shifting around a bit. But what you hardly ever find is species changing through time gradually and having those means of the distribution of normally distributed variable characters shifting in any one direction so that you can explain the origin of the next species just as a smooth outcome of slow linear transformation of a species. You almost never see that. Some people still say you see some. I don't even think you see any, but that's okay. You know, I'm an extremist. So it's stasis, the empirical realization that was known to Charles Darwin when he was 30, in his 30s, or late 20s and 30s. He knew about this. The other thing is, so how do you explain evolution? Because clearly life is diversified and has undergone a tremendous amount of genetically based morphological change through time. So how does that happen? It happens through natural selection, but in conjunction with a fragmentation of existing species and the modification of adaptations. And when I was a kid, looking to get my PhD and do my research, I was very aware of allopatric or geographic speciation as made particularly well known and I think analyzed by Theodosius Dobzhansky, who had been working for a time before I was there in the same building on the Columbia University campus, and also Ernst Mayr, who's most famous for it. So Dobzhansky wrote a book in 37, actually wrote a paper in 1935, which has got the whole thing going, about the importance of geography and the fragmentation of species in the evolution of life, and tied that in with adaptive change. And then Ernst Mayr came along. He was an ornithologist at the American Museum of Natural History, where I spent my career. Ernst was gone by the time I got there. He had gone up to Harvard, but I got to know him, and he was sort of the godfather, basically, of all of the systematists and of the living world, but also us paleontologists who cared about evolution. We turned to him. He was sort of like the wellspring and the guru of geographic speciation. So punctuated equilibria is the integration of the empirical observation of stasis as a common, if not the most common sort of way to characterize the history of single species. And when you get new species, they tend to bud off from pre-existing species, usually in rather small populations, I think. So that's allopatric speciation. So stasis plus allopatric speciation equals punctuated equilibrium.
Okay, that's great. So maybe we can summarize as morphological change is concentrated in brief intervals where speciation occurs.
Yeah, lasting. I think the key here is that morphological change can happen at any time, but it's going to just be, if it's incorporated and if it appears within the history of a species, it tends to get swallowed up. It doesn't last all that long. To have a shot at lasting through non-trivial amounts of geological time, morphological change should be packaged in its own community, its own genetic packaging. And that's all species are. Species are just packages of genetic information, where the breeding overwhelmingly tends to be among the individuals within that species and not between individuals of other species that might be closely related. Now, we all know that hybridization occurs and so forth, and sometimes it could even lead to lasting change. There's no doubt about that. But on the other hand, for the most part, the reproductive isolation that you get through geography, if the new morphology, if the new species, the fledgling species, survives, then it has a chance to be sort of injected into the phylogenetic mainstream of life. That has a shot at showing up in the fossil record as something that's different.
Okay. One more question. It's, what is the genesis of punctuated equilibria?
Despair and panic is the short answer of that. Because as I alluded to, this was not my first study, but nor my first publications. But this was my PhD thesis. I picked trilobites because they seem to have very complex morphology, more so than I was working on snails, gastropods before that. And the internal soft anatomy of a snail is complex, of course, but shells seem to be rather beautifully They grow in logarithmic spirals, and you can use a few variables to basically describe the variation, well, the nature of the shape of any gastropod shell. So I thought I had a better shot at documenting evolution because it already appeared that it's going to be difficult. It's just not a matter of just going there and climbing up a hillside and collecting fossils through time and seeing all the evolution going on. That wasn't happening. I already knew that that really wasn't happening. So if I pick something complicated like an arthropod that's well preserved, and I knew Bud Rollins, he was a graduate student 2 years older than me, and he came from Hamilton, New York, and the Hamilton group is as well known Middle Devonian, beautiful fossilization. And the other thing is that it has, we thought maybe as much as 8 million years, maybe 8 to 10 is what I thought. Now we're now talking 4 to 6 million years for the duration of the Hamilton group because of the refinements in geological dating. But I needed a system that had a lot of time, so millions of years of time, a good distribution in space into different environments. And the Hamilton fauna can also be found down the Appalachian Mountains and in the east of America, and mostly in muddy environments, but also in the Midwest, what is now the American Midwest, Michigan and Indiana, and well, not Indiana, but Ohio and Iowa, places like this where you have mostly limestones and limey shales and beautiful preservation of the same animals, you know, and supposedly the same species or in that same lineage. Work had to be done on that to document that more fully. And it seemed to show some variation and some differences. So there's some action going on. So I set up a sort of an experimental study. In a way, the experiment had already been run. I had to look at the results because I had space and I had time and I had complex anatomy. I knew that there was going to be some changes because already work had been done to show that these things were not all the same, exactly the same in these different places and in these different subdivisions of that time. And the subdivisions of the time and, of course, the reconstruction of the geography is independent of those trilobites. So I didn't use the trilobites to divide the time. Somebody else had already divided the time based on other fossil evidence, basically, and just plain old, good old-fashioned stratigraphy, and figured out the relationships in time of these samples as well as in space. So that was my system that I was going to investigate. And I remember, and I've written about this, being out with my wife in Michigan, in the central part of the United States, washing our clothing in a laundromat. And I pulled out a specimen of what turns out to even have been a different species, but you needed to have a microscope actually to look at the eyes. Including this, it was a gorgeous specimen, and I despaired because I said, I can't tell this thing from the stuff I have in New York. And where am I gonna? How am I gonna? When you do a PhD, you got to have results, and I was finding nothing. And it took a while for the penny to drop. The finding nothing was actually meaningful, and that was the stasis part of it. And okay, so I kept at it, doggedly persisting in my work and cleaning up the specimens and measuring lots of them. And there was a paleontologist, it still is, in England, Ewan Clarkson, who had been publishing on the eyes of very closely related castid trilobites from the Silurian of Great Britain. Gorgeous specimens, and anatomy is well preserved. And he came up with a different way of counting the rows, the columns, the vertical columns of lenses in the eyes of these, the schizocoral eyes of these phacoid trilobites. And I said, well, I'll try that. That looks like a handy dandy way for me to characterize sort of quasi-numerically. It wasn't linear measurement, it was counts of data, but get the lenses and count them and represent them that way. And then it tumbled to me one day on the elevator at the American Museum of Natural History that I should go and look at the geographic distributions of these different eye counts. Because there was something there. I kind of felt there was something there. And I had been a student of Marshall Kay, who was a famous stratigrapher in the mid-20th century. And he made us basically memorize North American geology. I mean, you know, he would say to you, all right, you go someplace and you put a core down in central Iowa. What do you see? I mean, what's there? You know, you tell me that. Then his real expertise was in highly disturbed rocks in the Rocky Mountains in Nevada and also in Newfoundland. But his geography was very big for him. So we basically had to take a map of the United States and draw where the states were, so that, you know, if we were going to draw a transect between Iowa and California, we had to know where those states were. So that was tremendous amount of education. And he gave us a bunch of blank maps of the United States. I had a bunch, and I started plotting the trilobite data on them. And lo and behold, I started seeing these patterns in space that made sense then. And you could see, looking at the waxings and wanings, the transgressions of the inland seas and the drying up seem to have a perfect correlation with the distributions of these different, slightly different versions of these trilobites. I call them subspecies. Now they're species. And so I put it on the maps, and bingo, the pattern emerged. One of your questions, I know, is going to be, is this a pattern or is this a process theory? And the answer is it's both. You have to see the pattern first. And the pattern is stability interrupted by rapid change geographically. And then if the species, if the fledgling, if the daughter species or the baby species survives, then you get this. And I insisted for years that you get overlaps in the stratigraphic range of the ancestor and of the descendant. So it looks like this through time. Now it turns out I don't insist on that anymore, because I think most of this happens in conjunction with profound geological physical events, and it involves very often, most instances, the entire fauna cross genealogically. It's not just one lineage that's showing this pattern, but they tend to do it synchronously or nearly synchronously with other elements of the fauna. And you get these turnovers. You get these étages that D'Orbigny in Paris freaked Darwin out with when he came up with the concept of étage. And looking at ammonite faunas in mainland Europe and saying, well, they go, that's one species, but there's other species, and they all tend to stay there and be the same through time. And then all of a sudden, bam, they're gone. And they're replaced by things that look similar but are describably different. And so then, is there a lot of time missing there? What's going on? Or is this a relatively rapid turnover, as Elizabeth Verba in the 80s was beginning to say? And we got the same factors, environmental factors, that driving extinction patterns are also driving speciation patterns. Just a great paper just came out last week or 2 weeks ago now on the great Ordovician biodiversification event. And it's invoking allopatric speciation as a means of, I think this is probably the greatest implication of all of the work that me and like-minded people has been doing, which is that the environment drives all of this. And until Elizabeth wrote that paper, in 1985, and I had to reread it to see that I didn't understand how that worked. I understood how the environmental change could cause extinction. I didn't see how it could drive speciation. Well, what it does, and Darwin couldn't either, and that's why Darwin knew about geographic speciation, but ended up pushing the other model, the linear gradual model through time. I didn't see how physical change in the environment, the way she said it was, it's simple, could drive evolution. It could drive extinction, but how do you get, is this just sort of filling empty niches? It didn't make any sense to me. What we're looking at, though, is the rearrangement of habitat space when you get physical environmental change. And that leads to fragmentation of species. It often leads to extinction, but it can lead to the generation at the same time of new species. And that's an integrated thing. And then, of course, some species can sail right through and they survive relatively unchanged on these events. We're talking about not global mass extinctions so much as regional extinctions that embrace entire species due to climate change or local catastrophes like volcanism or whatever. sort of intermediate level extinction and turnovers and generation of new species. But it has to hit, it goes to the point where entire species geographically are embraced in whatever the system, the systemic changes in the physical environment.
Okay, that's great. And for now thinking, you are already answered, is a pattern or a process, and I think
Right.
that's great. You answered the questions. You have to see the pattern and then come up with some process to explain the pattern, right?
Exactly. Yeah. And I am content, I still am content to use allopatric speciation, which comes from the biology consideration studying of the recent fauna, and also the basic syllogism of natural selection, working on ground mass of variation. Um, this is a hot news flash. I've been working with some geneticists recently and looking at the distribution of mutation rates, and I'm beginning to see some patterns there now. I won't even say what it is. It's very exciting, though. It seems to fit these periods of rapid change that we see occasionally punctuating the otherwise long, boring history of stability that you basically see in life. And we all
All
love
right.
stability. We all wish that we had more stability in our social systems and in our lives right now. You know, good old stability, because you can then do whatever you want to do and not worry about things. But now we're in an immense, a period of rather immense instability. And anyway, that's a different issue. But it's the same sort of thing. We all like stability. I think brachiopods like stability as much as we do, you know.
I think so. Um, by the way, I think I saw a paper by, I just remember Eugene Kooning. Eugene Kooning was a paper about the main mode of evolution, and it's consistent with punctuated equilibrium. But I don't remember the details of the paper. It's a highly technical mathematical paper. Was
Yeah,
published
I think
this
all,
year.
yeah, is published this year. Well, if you think
Yeah,
of it, please send it to me. I'd like to look at it. It's very
I'll send it.
interesting that ever since we started talking about this, I remember there's a macro evolution meeting in Chicago in 1980. We published punctuated equilibrium in 72. I had published already the gist of it in 1971. So it was controversial in the 70s. It was a lot of fun, and it was a lot of angst and a lot of argument and everything. But one of the themes was people would walk up to me, sometimes paleontologists, and say, "Oh yeah, you're right. Yeah, I've seen this all along, and I know you're right." And a lot of people were very angry and saying, yeah, "You're wrong," and all the rest of that. But I would get other people, like molecular biology was just getting off the ground, and they were just beginning to look at Gabriel Dover came up to me, for example, in 1980 in this macroevolution. This is, I have the explanation for punctuated equilibrium. It was about the newly discovered transposons giving you rather sudden pulses of change. I said, Gabe, that's fascinating, and you might be right, but I have no evidence in my data that allows me to really evaluate that. And by the way, and this is before I was even thinking this way, this was 1980. By mid 1980s, we could see that most of the time when this was happening, as I said already, in one particular lineage, it was happening in other lineages more or less at the same time. So it was ecosystem wide, regional ecosystem wide kinds of phenomena that was going on. And then if you try to use a causal explanation derived from the biology from within the body, like a molecular genetics explanation of it, you have to have one that would be responsive to external environmental change affecting more than one kind of species, not just intrinsic to one species. And that's a tall order, although people are beginning to do that. So it's, we don't, we're just, this is just where we are now. And not all, it's been difficult to convince biologists, people who do not look at the fossil record, are glad that they don't, I guess. Um, to persuade them that stasis is real. That's why we did a paper in 2005 with John Thompson, who's a geneticist, ecological evolutionary field-oriented geneticist. Basically, we got to talking in Brazil, in a meeting in Brazil, and then we put together this group of half geneticists, half paleontologists. The main difficulty was persuading the geneticists that there was a problem there at all. But anyway, we succeeded reasonably well so that we could then write the paper about, let's say that stasis is real. Why do we get stasis? And looking into that. So I think that was a hallmark of what it's saying. But what I started to say is these are all progress reports. That's what science is. This is what we think now. And of course, it's not unanimous. I got off on that point too. But from the people who see the world to be structured the way more or less the way I see the world is structured, there's disagreements, and we know that we don't have all of the answers about if that's true, why is it so, and how does that actually work? But more and more, I am convinced that it's all driven by the fact that organisms are alive but living in the physical world. There is a lot of coevolution. There's a lot of biotically driven patterns, but then they're not the main signal, as far as I'm concerned, in the history of life.
All right, that's great. The next question is, you already mentioned this, but why? What do you think about this? Why did punctuated equilibria stir so much controversy in the 1970s? And still today, I think.
Well, people are very conservative, and all the money that flows through science is very conservative. And basically what you're doing is disagreeing with Charles Darwin, the patron saint of everything. Although I think he loved Lamarck much more than people tend to know. You mentioned that Eternal Ephemera book. I learned so much when I did the research for that. I particularly liked the early part of the story and how these guys got going but they were going against prevailing religiously based belief. And that was even harder. But we were doing something not as hard, but we were seemingly disagreeing with the great Charles Darwin. And everybody was bending themselves into a pretzel, as we say up here, just bending all the way to explain their patterns consonant with what Charles Darwin said must be true. Even Dick Lewontin, he never got it. He never understood it. It was frustrating. And I said Steve Gould was teaching with Dick, but I never really asked Steve about this, but Dick never understood the patterns that we see. And so people thought it was an artifact, the bad data, that they all just said bad data. They all, and this is what even Dobzhansky and Meyer were saying about the fossil record. They had their sort of punctuated patterns of the interruption of gene communities in the living biota that involves time, but not so much time. But then when it came for them to wave their hands around and say, well, how does this work out for explaining the history of life in general? They reverted back to what I call the rabbit ear and like a TV antenna. Here we go. So here's pretend this is an old-fashioned television set with the antennae to catch the signal on the back of the TV set, and it collapses down. But when you have it out to catch the signal. So this was I think it's the TV antenna model of evolution, which is that you get allopatric speciation down here. You get one thing splitting off because clearly life has diversified. It's not all just one species out there. So there they do it. They got a good explanation for that now. But then they were content to say Simpson and Meyer and Dobzhansky, not so much George Simpson, that then after that you get gradual diversification and it looks just like Darwin. So that was the basic model that we all grew up with as a result of the modern synthesis. We were the next generation after the modern synthesis, basically, late 1950s into the early 60s. This is what we had. And if you look at the textbooks, this was the model that was presented. So Darwin was in the main preserved, and Darwin knew life had diversified. What Darwin didn't know about was what I said earlier about how physical environmental change does occur and what it does to environments. He could not see when he was standing on top of the Andes, looking back over towards Brazil in northern Argentina, basically. Then, but he had been in Brazil in Argentina. He knew that the fauna, as soon as you get out of the Amazon basin to go south, you get more or less the same stuff. You get the same guanacos and you get the same rayas, except for fortunately there's two different kinds of rayas in there. But he could see the continuity, and he was very worried that he wanted a theory that fit the greatest number of examples. He knew about speciation on islands because he had his own data for that, and that's what convinced. But on broad expanses like the lower 2/3 of South America, from the Atlantic over to the Andes, he struck him as sufficiently homogeneous in the distribution, the same 4 species of armadillo, or 5, or whatever they are. He saw in eastern Argentina, as he saw over at the foothills of the Andes, and it just kind of freaked him out. He did not understand how isolation could occur under those broad expanses, because there was not even a theory yet of glaciation, let alone the sense that there is fragmentation through physical and reorganization of habitats through physical environmental change. And he didn't know that because science in general hadn't caught up to that yet. So, I mean, Agassiz, who was against evolution, came out with his glaciation ideas, I guess, in the 1850s. Anyway, too late, basically, for this to really impinge too much on Darwin's thinking. So anyway, that was my story about that. But I still think that that's where my head is at these days, because we're dealing with global climate change. We're seeing it sloshing, I would say, up until recently, around our ankles. It's up to our knees now. It's incredible. It's occurring much more quickly than in the 90s we thought that it would occur. Nobody had any idea that the climate change is hitting us so hard. But I think that is the story of the history of life, is climate change, basically, and other physical events that drive it. I know that I'm drifting away from whatever the question was, but
it's okay. It's okay. But one thing when I read your book, I was thinking, you wrote, and I totally agree. It's really hard to understand how Darwin ended up a gradualistic, because he had phyletic gradualism. I think Pontuado Equilíbrio, we can say in some way it's still gradual, because it's not like a species bud off immediately in the next generation.
No, there's a very rapid but purely Darwinian, I think, processes governing that. That's the internal syllogism of the 3 points of the natural selection, the way he laid it out. We know why we know more about why organisms do resemble their parents. We know why there's heritable variation, and although we don't know as much as we think we do, and I think our paper that we're submitting this week is going to help clarify some of that. But anyway, as I say, we know a heck of a lot more than Darwin did. But the fact that there's a limit to reproductive, just so that it's competition for resources out there, it's a law of nature, the natural selection, and that still operates, but it operates very quickly when it's happening at all, and it makes these new species, which are packages of genetic information that are like gene banks, and if they survive, then we've got a new package of information involves a modification of the adaptations of the component organism than what they came from. Right. But it's rapid selection in particular circumstances that ends up making the lasting change. Yeah.
Oh, right. But the point I was making, and that you make in your book, is that Darwin had actually not no evidence that evolution was gradual. He just drifted to that point. He in some
Well, the way he put it was logical. He said, we have two things: we have space and we have time. We know that space works, but I can't see. He didn't write this out, but he couldn't see how it would work over these broad expanses. And since he couldn't see that, he says, we'll go to the other thing, which is time. If you go through time, there's enough time for, and the analogy was with selective breeding. Eventually, you will get a modification. And his principle of divergence, which nobody ever cites, is the reason why he had that one illustration in The Origin of Species. And the fourth rendition of that, I never published this, but I worked on it with David Cohn as a historian. I guess I have a little bit of it in Eternal Ephemera. He saw that diversification could go on within species, and then the more highly diversified, maybe superior in some ways, subspecies, races, whatever, that would diversify would come back and outcompete the more primitive ones. So the children within a species, the children would basically kill off their parents. And it was all biotically driven. That's what he did, to give you that sort of pattern of diversification. And he would be comfortable with, he knew about stasis. And in one sentence in Notebook E, he actually says, if space is more important than time in the history of life, then that would mean that I know how that happens, and it explains why species are so damn stable. He actually says that. In another part of his notebooks back in the 1830s, he says, surely Mr. Lonsdale, who was an invertebrate paleontologist of that era, British, has examples of gradual change through time. And we never hear from Darwin again about Mr. Lonsdale, because Mr. Lonsdale did not have any examples, you know. So there you go.
Yeah, that's it. And somehow he ended up a gradualistic and like Lamarck, but he was not that willing to say he had some of his ideas from Lamarck gradualistic view of evolution.
No, although he does in Notebook B, which I think is his best writing of anything, when he looks at these two, space and time, he has very good things to say about Lamarck. And it's obvious. People tend to think that Darwin got his gradualism from Lyell. He didn't. He got it from Lamarck, as you say. And Lamarck just thought everything was gradual and didn't show up in the fossil record. So only 3% of the things that the fossils, the kinds of mollusks that you could find in the Paris Basin, which we now know to be about 50 million years old, only about 3% of them show up in Lamarck's viewpoint in the modern oceans today. And the rest of them didn't go extinct. He was fighting with Cuvier about that. Cuvier said, oh, most of the things that you see in the fossil record are extinct. And he doesn't say how we got the modern things and where they came from. So we don't know. But Lamarck said, oh no, they didn't go extinct. They transformed into the modern versions. They're similar, but they're not the same. And we don't see them in the fossil record, which is the viewpoint. Basically, Lamarck's viewpoint about the pattern is what most biologists will tell you as a knee-jerk reaction. The fossil record stinks and we don't see the transitions, but otherwise, in principle, they were there. And that's what Lamarck was saying, and that's what Darwin ended up accepting, because he was throwing up his hands in despair. But it was an honest search, basically, for the most general explanation for the history of life. That's what Darwin was after, and that's an admirable thing to go to. Yeah, I'm glad he made the mistake. He followed the wrong path, and so it gave us something to do. I mean, that's
it's a
if
gift.
he hadn't done that, and Meyer and Simpson, Meyer and Dobzhansky hadn't done allopathic speciation, and George Simpson also on a larger scale talking about abrupt patterns of change, hadn't done that work, there would have been no punctuated equilibrium. We just came from all of that. Just trying to correct the perspective. That's all, a little bit.
Okay, that's right. I think you answered it to this at the beginning of our conversation, but which you think explain better the history of life? It's punctuated equilibria or phyletic gradualism?
I think it's basically driven by environmental catastrophes of different orders of magnitude, from ecological succession, because there's a local event like a local lava flow or something like that, wiping things out, and it's colonized in from living species. And this, then I would say there's not much evolution. And then my friend John Thompson would say, oh no, there's always genetic evolution going on. So I have to be careful and say lasting morphological change, not triggered by that. You have to get up to basically the tipping point, which is the existence of species as reproductive communities, shared adaptations for reproduction. So most of the reproduction is going on within and not among species. You start messing with those at that level and driving some extinct, that's when you get evolution kicking in that has a chance of lasting and making new species and so forth. So I think the whole history of life is punctuated at varying orders of magnitude. That's what I think. And when change occurs, it happens through that basic syllogism of natural selective type processes. But it's complicated. There's other complications, and I am aware also that there is a way of thinking about evolution that says it's ecology acting on development, and I like that, and I get that. So I don't think that's all been integrated as well with as completely as it might have been, or maybe will in the future. So there's a lot more to learn. But yeah, but selection itself is generation by generation, and it's not just saltational the way some people have thought. But it can be so rapid that it looks saltational in the fossil record. Let's put it that way.
Okay. So next question is a question from my advisor, Felipe Pinheiro.
Okay.
He's a paleontologist. He works on pterosaurs and archosauromorphs from the lower Triassic and great paleontologist, my advisor. The question is, you think episodic sedimentation poses a problem to the theory of punctuated equilibria?
No, I think that we have to be careful of our samples. When you have physical events, very often they are correlated with hiatuses and depositions and so on. My advisor was a great paleontologist, so Steve Gould's advisor too, Norman Newell. He wrote a whole series of papers when he started talking about extinctions being real and mass extinctions in general being real and of major significance to the history of life. He started paying attention to unconformities and paraconformities, and he said, yes, his notion of paraconformities was depositional hiatuses that don't even meet the eye. If you just look at the rock record, it doesn't even look like there's a depositional hiatus. But yes, so we have to be aware of that. And be very careful about that. But my standard answer is, in the rocks that I worked on and anything else that I've learned about, is stasis. Is
Can you repeat? You were saying my standard answer and then it froze.
Okay.
Can you?
My standard answer is that if you sample up a cliff face, there are lots of depositional hiatuses. Assumingly, and you don't even know for the most part where they are. But if you collect up, and if you can't tell the fossils from the top part, then from the bottom part, it doesn't matter how much time is missing.
It's a stasis.
Yeah. So, and I can point to areas in the Midwest where we know there's time missing. Because of the way the rocks correlate with the more complete sections in the east, where the deeper basins were. And we can still see that very often, once deposition resumes, it's apparently the same animal. And again, how do you know it's the same animal? Because maybe the soft tissue is changing too. But the point is the external morphology evolves. And that's the problem that you're trying to look at, is what is the pattern and likely mechanisms for the morphology that is preserved. That does evolve. That morphology evolves. And it shows these patterns of stasis, but also it changes over considerable amounts of time. And what is that pattern? So those are my answers to, and how do you know you're dealing with real species? I might as well tell you my standard answer to that is, if you imagine going to a beach and collecting along the strand line where the tide is putting the shells, and you sort them, and then you go out and do the sample the living biota and do the anatomy and the genetics now on the living organisms, you will find they are separate species, and the piles of shells that you make agree with the species that you find living in the waters just off that shore and producing those shells. And my point is, if you make those piles of shells and then you have time and fossils, which Darwin saw, the first observation in the Canary Islands is that the same shells were in the rocks as were on the beach. So he knew that. He absolutely knew that. It was only when he got to Argentina he started seeing the mammals are different, but the shells are the same. And Monte Hermoso, you get the same shells, the same, and that was called the same species. But we know they are the same species. If they look like the same shells that you're getting on the beach today, they are likely the same species as they were. What does that mean? Is the genetic change accruing? Sure, you're going through time. Nothing is utterly stable. This constant flux in the genome. But we're talking about patterns of evolutionary change, of preservable morphology, and that's why we think we're dealing with real species as much as you're dealing with real species when you sort shells on the beach.
Okay, that's great. So just put an aside here. Not exactly an aside, but Darwin was particularly fascinated with that case of a cavy. I think
Yes.
it turns out it wasn't a cavy at all, but
no, it was a chinchilla, I guess, or something.
Yeah.
It wasn't. Well, it wasn't. He thought it was the. Oh my God! It's like the mara, what they call the mara, and it's the third largest rodent. Patagonian. Wait, it's the Patagonian cavy, but it's the third largest rodent in the world. We did manage to see some when we were there, but they're being driven extinct right now. Yeah, and I didn't realize until I was going through my PowerPoints to give a speech right after I retired up at the Paleontological Research Institution. That morning in the motel room, I reread what Darwin said about it, and he said in his notes, it's a species lesser than the current cavy, the one he found at Monte Hermoso, which turns out to be older rocks. They're Pliocene rocks. They're not, as you say, they're caviomorph rodents, but they're not this big cavy species, the mara, at all. And there are real mara in there, and they are the same, actually. They don't change. But he said, aha, I think I've got the same thing, but it's smaller. And so he was actually seeing it as a smaller version of the living thing. And that was in his mind an example of change. And he was desperate because the shells don't seem to show that. At Punta Alta, the other locality, the shells were mixed in with some of the bones, and they were the same as the living ones. But the mammals are different. A lot of them are extinct. But here is one that seems to be still alive, but it's a different species because it's just a bit small. He was wrong, but the point is, what was he thinking? And he thought he had an example of an ancestral species. It's important. It doesn't falsify the thought. but it's what he thought based on what he thought, based on what he collected and his interpretation of what he had. Yeah.
Okay, that's all right. Somehow, maybe he was already thinking about evolution. Yeah.
I think he was as a kid in Edinburgh, but I can't prove it, so I won't insist on it.
It's really
I
hard to
think
prove.
the kids had a research group that Jameson had, their geology professor, had founded, but was not, I don't think, an active member. So the kids, it's like a seminar group or an informal group. We did the same thing with Steve Gould and Bud Rollins and other people. I was still in college, and these new graduate students showed up, and they were interested in all sorts of things, including, of course, evolution. Excuse me. And so can you still hear me? Yeah, okay. So we had our group, but Darwin was in a research group with students and presenting the results of their research. Darwin had been going out with Robert Grant and collecting bryozoans and studying them and so on. And back in those days, almost anything you saw and described reasonably carefully was a contribution to science because nobody else had done it, So it was great. They were talking amongst themselves. They in Edinburgh, they were very aware of the French line of thought about Lamarck, but also Cuvier, and I think Jameson was very actively encouraging that. So I think that Darwin knew about evolution as a possibility, and the first thing he did when he got off the Beagle, and that was in 1832. January or February in Cape Verde, he compared the fossil shells that he found in the limestone that was capped by was preserved because it was capped by a lava flow. So it was not just yesterday, that rock. And it was at the beach. And he had shells there, and he couldn't tell the shells in the rocks from the shells on the beach. So the very first stop, he's looking at time, and he's looking at the patterns of are they the same or are they different? And they were the same in this instance. And so, yeah, he came with that idea to do that kind of thing. And I think it went all the way back to the mid 1820s. After all, he had read his grandfather's book. This was all in the air. This was all in the air. And he read Lamarck's invertebrate monograph, which is more important than his 1809 book about these things, in my opinion, 1801, talking about the mollusks and coining the word fossile in that book. Darwin had read that, and yeah.
Okay. Let me see. One question I think I have just to do it, and we already these questions and another one, and we're finished. Okay.
Okay. Sure.
The question is, what do you think was Steve Gould's main contribution to punctuated equilibrium?
He named it. What happened was he said he wanted to get into Tom Shop's program of having a meeting and then producing a book to try to inject more theoretical perspectives in paleontology. And he heard about that, but he wanted to do morphology and something else. Oh, I guess systematics. And those topics, Dave Raub was doing morphology and Mike Gieselin was doing systematics. So, and evolution, I guess, more broadly. So the only topic left over was speciation. And Steve said to me, and he had already seen a final draft of my manuscript for a paper called the allopatric model in phylogeny and Paleozoic invertebrates that ended up in the journal Evolution, which sank without a trace because most people didn't even see it there. Most paleontologists didn't. Anyway, I was reaching out to the biological audience. Anyway, so Steve said, he said, I can't really think of anything that other than what you've written, basically. So why don't you join me? And I wrote most of that paper, but he wrote the introduction and he put it into good philosophical and historical perspective. And then at the end, we both contributed something on implications. I did the thing on trends and on sort of like Steve Stanley ended up calling it species selection. And I think Elizabeth very usefully said, well, species sorting, and maybe it's selection, maybe it's not. And the argument, I guess, persists about that. But Steve talked about the radiation of, I think, of lower Paleozoic echinoderms, and he had some really good insights in there. And so basically what he was doing was extending the model to be more generally embracive. I took it up a notch and said that species themselves might be sorted or selected. But he said, yeah, but look at these large scale patterns of diversification, and the pattern seems to be general. And so that was extremely important that he did that. So, and I think the arguments that I originally had with my example, which we put in there, we added Steve's snail's Bermudan Pleistocene snail example, which I actually wrote based on his published work, to show that it also fit the model fairly well. But I think talking with him, he tightened up the argument and he made it, I think, more general and more relevant to the world. And certainly he was already attracting attention in his natural history column. And so it helped get it out there too. I mean, that was a major effect. So, and also I was initially inspired by Steve because he was telling me a couple of years before, while we were students, he said, we have to start thinking theoretically, and we shouldn't wait until we're 60, which was the age he was when he actually died. But of course, that was down the road. So so he was very encouraging. We should start publishing. We should start thinking. Our thoughts will never be fresher than they are now. So that was an inspiration as well, a more general inspiration, but yeah, it was there. So that's this thumbnail sketch of that part of the story with Steve's involvement.
Okay, that's great.
What was the other question?
The other question is again about Steve, Stephen J. Good. I don't know if I can call him Steve.
Steve. He was a kid from Brooklyn. He was a kid from Queens.
Queens. All right.
Yeah.
About Stephen J. Good, you wrote in Eternal Ephemera that, quote, you had never met anyone as smart as he who worked so hard, and you think remains true to this day. I am an admirer of Good's writings. I have some books. I just buy the 4 of them to read.
Yeah, great.
And I can't help but asking, what was like working with him? He was that smart, focused on his work, and what was like?
I gave you a partial answer when I said that he was inspiring. He was saying, "There's no time like the present, and we're in this to play the game up to the hilt, and not wait until we're old people to start dreaming up theories explaining everything. We should be doing that work now as the immediate goal of what we're doing." So I think that's a great example of what it was like to talk to him. That would be, we had offices in a little semicircular building that stuck out from Skirmahorn Hall, sort of a rotund, well, I don't know what it was. Anyway, I would get bored or tired in my office. I'd walk over and start talking to Steve, and he'd be in there, and he was working on his biological reviews paper on growth. And I said, "Why are you doing that? You should be working on your thesis." He said, "Well, this is an opportunity I can't resist. I was invited to write a review paper on allometry." So he did that, and again, that I saw what he did. The museum is 40 blocks away from Columbia University. Maybe it's not 116. Yeah. So we would take the bus back and forth between the American Museum of Natural History and where we did some of our graduate work, and Columbia University main campus where the geology department was. And he was never at a loss for words. So what he would do was give an impromptu lecture to whoever of us was on the bus with him, whether it was just me or whether it was just somebody else who knew but not me, or whether it was a small group, as it commonly was, going down for a seminar and then coming back. And he very often, not invariably, but very often had something to say based on what he had just been reading. So when another mentor of mine, Marvin Harris, stopped writing the column for natural history, by this time I was already employed. I was a student there at the museum, but I was already employed at the museum. And the editor of the magazine said, who do you think I could get to replace Marvin as the monthly columnist? I don't want to drop the idea. I said, I got the perfect guy for you, because he's never at a loss for words. He tells us a story every time we get on the number 11 bus to go up to the Columbia campus or come down from the Columbia campus. And he's incredible because he's very, he tells a story very well. And he's impassioned, he's passionately interested. And he's got his antennae sticking way out all over the place. He sees stuff that the rest of us don't see. And he sees the implications of things. And he makes a great storyline out of things that come in. He's always got fresh material. So so that's what happened. And he started writing that column. And he basically, when he got older and he was on the Harvard staff, he had assistants to actually help him gather that information, find it and gather that information. And he got very smart about organizing his books. And I said to him, I'll bet you're writing your columns now with knowing that they're going to be gathered together into a book, so you can thematically join them together. That's not just random. So he gave a lot of thought to that. So he was a role model from in-person, just conversation, to watching him work from a distance or just across the hall or even from a distance at Harvard, and sometimes asking him what exactly was he doing and what was his approach. And am I right in supposing this or that about what he's doing? And he would say yes or no. And we would talk. So we stayed in touch for the rest of his life, even though, and we wrote a couple of things together, but it was, and he would come to New York and we would get together. And then he finally moved back down to New York. So we stayed friends, but it was the way friends are. I mean, you don't always talk shop. Talk about other things. Talk about politics. Talk about art. Talk about, you know, so. But he was very free and easy with his conversation, always willing to talk.
Okay, thank you. I think that we can finish this conversation here. And thank you again. Thank you so much for accepting my invitation. I think that's really, really great. Never thought I would be talking to you one day, but
so,
it happened.
Well, it's the miracles of modern technology.
Yes, yes. Modern technology is indeed a miracle for good and sometimes for evil, but
exactly
the way the things are. So I think that I hope you guys who are watching this conversation enjoyed, and if you like it, like button here, subscribe to my channel and to Eldredge's channel. It's called Niles Eldredge, right here on YouTube, your channel.
Good. Yeah.
And I'll leave a link below to his channel or a card here. I don't know. And thank you, Dr. Eldredge.
My pleasure. Lots of fun, and I have some buddies in the Bahia and the rest of Brazil. So yes, I've been since 1963. So and I wish that Darwin had gone there and Beppe would have seen those Pleistocene fossils even sooner. He had a way to
that would be great.
Yeah.
So. Yes. So well, we're done here.
Thank you, Juan.
No, thank you. It's a honor. It's a pleasure. Okay, guys, we're going in 3, 2, 1, bye. My hand
Bye.
here. Bye.
Bye-bye.